All right, how we doing, y'all? Good? Pain? Happy? Tired? Wednesday? Hump day? Middle day? The day after Veterans Day? 11/12/2025, whatever you want to call it. Day I can just escape from home and come to class and socialize and realize everyone else is socially awkward too. I don't know, just whatever you want. All right, how's well, I guess the lectures. What do you guys think? If honestly, if I had my own lecture notes, I would have done it a lot better. We'd be just doing MATLAB in class, showing you guys examples, running them, bringing your laptops, and we would just be like, "Oh, we can move poles. I want you guys playing with poles because once you understand like the Laplace transform, M, S, right, and real S, you can start realizing, hey, if I just dance this pole around, well, there's another pole over here too, poles or conjugate, right? And then and then there's a way where you can just easily integrate this to be some like signal, I don't know, val, or I don't know, f of t, whatever, t. You can see some ringing, or I think that signal is going to look like this. I don't know. It'd be so cool to just move these things around and be like, wow, I'm getting my money's worth, okay? That's what we're going to try and do today, all right? So you guys got to see in Laplace, they're not that bad. There's just that ugly integral. But after you start memorizing that table, it's not that bad at all. So, and then, what do you call it? There's the property about differentiation, derivatives, right? Got to memorize that one with the initial conditions, the unilateral Laplace transform. That's going to be on the exam. Okay, memorize that. If you guys want tips, please do the written homework. Start with the end. Okay, start with the end. All right. Start those last problems, not just go backwards. Okay, one page, last problem, second to last problem. You realize the last problems are usually what your exam is going to be based off of. Okay. And then inverse Laplace transforms, well, if you memorize how to go from time to Laplace, then you can go from Laplace to time, but how do you do that? Partial fraction expansion, okay? So you're gonna have these ugly equations, they're just big S polynomials, but you realize if you just have it in the form of, if I were to describe this system, I don't know, R1 over S plus A1, right? Plus R2 S plus A2, correct? And then you start realizing you can just transform this into R1 e to the, what do you call it? A1t, right? Plus R2 e to the A2t, right? Making sense? And then don't forget this, okay? 2 points. I don't know, I'm just guessing. No one's gonna forget that on the exam, right? You guys like that exam review? Does he tell you guys the points? No? You guys happy that I can tell you? You guys see how easy easy the effort when you know what's going on, okay? There's the little fundamentals. I think he gave you like 3 bonus points if you just wrote convolution on the first exam. Was that great? See, it's these little points that it's 1 or 2 points, but they add up a lot, so... Anyways, everyone familiar with what's going on, all right? So this is not going to be that bad of an assignment, so that's why, and oh yeah, I still have the notes open. I never close them. Let's open up MATLAB. Who's ready? Why did the CD drive open? Anyways, let's go over your assignments so that you guys have a better time. Okay. Focus, there we go. Come on, MATLAB. Oh, that's because I don't have power. I don't want our laptop to die. Okay. Just put this charger. See, there's always one thing I forget. You know, there's 1,000 things you forget every day. Make sure this ain't one of them. If anyone knows where that's from. Anyways, I started the computer assignment for you because I'm too lazy. just walk over. So let's see. Let's go over this computer assignment. Is this it? No, that's not it. Is it? Yeah, let's go. So you guys see like the answer. You can get all the answers just by reading this piece of paper. B of 1, S of M, right? Nth pole, right? Or mth 0, nth 0, right? Down to whatever you want, your polynomials, right? Is that good? Then you got polyval. System function can be evaluated for particular values of S using the polyval. BS, polyval AS. Okay. Wonder what it's doing right here. Polyval. Okay. See, this is where help polyval. Let's see what it does. Polyval returns the value of a polynomial p evaluated at x. Okay. Oh. So if you put 0 here, just punch in 0 everywhere here. Okay. Yeah, it's literally what this does right here. Is that what I want you guys doing? Px. Okay. Maybe there's a way to do this. Can be evaluated along the x-axis. Okay, boom, boom, boom. System can be run. Okay, yada, yada, yada. Gains. You get your z-plane. Okay, generates the pole 0 plot for this function. Cool. You got these the zeros. You got your poles. Boom, boom. So you can do the z-plane two ways. You can just plug and chug this polynomial, right? Pretty ugly, right? Or if you already had the zeros, right? Your zeros and your poles, you can just punch it right in and it's the same thing, okay? So if I wanted to pull at, I don't know, -2 and -4, well, right here, -2, -4, boom, I'll show you what I mean. Copy, boom. Let's ignore this for now. Boom, boom. Let's see what this does. Yeah, look at that. You like that? Now I want to make these poles dance a little bit. So I'm going to make this -2, right? 4. Now watch this middle pole right here. See, it moved. Ooh, it canceled. Ooh, that's pretty good. What other things can I do with z-plane? Because I don't like that. MATLAB z-plane function. How do I make this colorful? Because I like colors. Make it colorful. Make it big. Ooh, look at that. What does this look like? Magnitude response. You guys don't know that, but you guys will eventually. For discrete systems, there's a discrete Fourier transform. It just repeats around the circle. And then this right here is DC, and then it's a bandpass filter from this, right? It's bandpass. Heck yeah. Yeah, you guys can't wait till the day where you look at this and be like, it's just a bandpass? How did I know that? Experience. And then you got poles right here. What the heck is this? So you have a big magnitude here, and then there's zeros over here. So it's like a weird, it's a Chevy Chev. Yeah, it's a Chevy. You know what a Chevy Chev filter looks like? Looks like this. See? Wiggles. Anyways, let's keep going. How do I make this colorful? I don't want to waste time. But do you guys understand what's going on right there? You can move your poles and zeros easy. All right, next step. Your assignment. Give you the answers. Roots, poly. Remember this right here? This is your goal, okay? This is what you got to do. Residues, poles, and your gains. Who cares? Well, me. I don't know. I don't really mind it. And then B's, A's, you can run this, get the residues of this, right? And then run this RPK, right? And then run a Kronecker delta. Guys, remember what the Kronecker delta was? It's the delta in time, or in terms of like the n time, or discrete delta function, Kronecker, okay? Poles times residue, right? E to the pole t. Make sense? Let's see. Then how do we do this problem? You guys remember how to do it? Remember the derivative property you guys going to memorize, okay? I wrote this right here. See? This converts to, well, this. Okay, this is why I don't like doing this. I changed it to where I said write this, but I wanted to see what you guys wanted to do. This is, I don't know. I just created this BS. Let me show you what I mean. Problem 1. Bring my camera. Boom. There we go. Is that better? Y double prime plus 2a prime y prime plus a squared plus omega naught prime or squared y is equal to x prime plus ax. All right? You guys remember the rule you guys got to memorize? If you have d, what do you call it? dn dtn, right, of y, right, just converts to s of n ys, right? Remember that? Easy stuff. Okay? So if this is a second order, right? Second order output, right? That just converts to s squared y of s, correct? Plus 2a, we got s right there, right? ys, right? Plus a squared plus omega naught squared. This is just y of s, correct? Is that good? Is equal to s of x, right? For that one. Let's do a different color. Do blue. We're doing this part right now, right? S plus, or x of s. S x of s, right? Plus a x of s. Is that good with everybody? All right, now let's just start moving things around. So if I were to start with this guy right here, right? What can we substitute out, or what do you call it? Get out of the equations, just the y of s, right? S squared plus 2a s plus a squared plus omega naught squared, right? Is equal to x of s, right? S plus a. Looking good, right? But we need our transfer function, right? Which is equal to y of s, right? Our output voltage over our input voltage or currents, whatever you want, right? So we get this. Just divide this guy right here. Move that down here. Just divide it and then just move this guy down there, right? Easy. S plus a, right? S squared plus 2as plus a squared plus omega naught squared. Boom. Boom. Done. Number 1's done. Oh, sorry. Let me just do this. Is that easy with everybody? Everyone got number 1 right? Not too difficult, right? Can you do this? So that means you can get, like, remember how it was like 3 or 5 points? That's 5 points right there for the 5th exam. Okay? And I think you guys are going to get like 2 of these problems. I think. I'm not so sure. Anyways. Boom. You got it. That's what I tried doing right here. Here's a comment. Copy that. Have fun. And I just wrote the original problem. Like that? Anyways. Now we got to start drawing stuff, okay? S is equal to that. Using MATLAB, calculate h of s. Plot h of s. So I was trying to do this, where I was trying to create an whole S domain. But let me see. I wonder if I can do... Because this right here is the real values, right? And this right here is the imaginary values. So I was trying to do this, mesh C. MATLAB mesh C. It's requiring X, Y, and Z. Oh, we got to evaluate things. Okay, cool. Cool. Mesh C creates a contour. Okay, there's one thing we're missing. me show you this. So these are just vectors right now, okay? Just a linear vector. But we need to make this a square, okay? So it's like a square. Instead of it being two lines like this, we got to like extend the square. Do you know what I mean by that? So right now, this is just a 1 by 10, for example, okay? I'm just saying the number. And then this one here is going to be like a 10 by 1, right? Well, we need to make a square, a 10 by 10, like play field, okay? So we got to set up our play field. But then we need to start calculating this by, I don't know, whatever our h is, okay? Just throwing that number out there. A value to assign to that point in space. Here's the x-axis. Let me just show you. Does anyone bother if I do this? X or that, or S, x-axis. Does anyone bother if I do that? Does that make it clear? Or does it make it harder? No? X-axis and the y-axis, okay? Should I keep that name or should I go back to im and a real? I'm going to go back. I don't like that. That makes me confused. There we go. Real, imaginary, okay? Real, imaginary, and now I need to calculate that, okay? So let's do it. H is going to be equal to, well, we got, I don't want to solve this. Well, we did have this puppy right here, right? System can be evaluated, every point can be evaluated using this. So if you think about it, if we get B's, right? What's our B? Boom, 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 up to that. So you know what I'm going to do? I'm going to do B is equal to, this is our zeros. No, that's not it. It's going to equal to S plus A. No. That's not what I want to do. 1 and A. There we go. And A is going to equal to, what do you call it? 1, 2 dot times A, and A dot, there we go, period, plus omega 0 dot times squared. Right? Is that good? Third order, so where does the 0 go? I think I want to put the 0 right there. Okay, does anyone understand what I just did right here? So why do I have 0, 1a and not 1a, 0? Because we're doing it based on powers. Do we have an s squared in the top? No, we have an s here, right? We just have a number here. S squared, number, or s, and then some number, right? Is that good with everybody? Easy? Okay? Don't forget your semicolons. We don't want any ugly code. Anyways, we got S real, S imaginary, but we need to run this using S. So if I were to do the following, S is going to equal, let me see, I need a square. Where's our square value? I think I gave you guys that function. Mesh C title, X label, Y label, Z label. Let's see, how did I solve this? Because this right here is going to help us evaluate that actual thing. Because we just need to do poly val B S, right? Dot divide poly val A and S, right? That's all we got to do, correct? That's going to evaluate our thing. But this needs to be a square, so let me see. Mesh grid, is that what we got to use? Help mesh grid. Maybe I should have put that there. Mesh grid, Cartesian rectangular grid in 2D or 3D. Okay. Let's try that. S. No, because I want a square. 2D, 3D. No, I want a whole grid. Mesh grid this. That's not what I want to do. Because I have these polynomials and now I want to solve for it. You know what I'm going to do? Let's comment this out. Let's do A is equal to, wait. Can't do that. A naught. Okay, someone's going to make a mistake here. See that A right there? And we're using the other A over here. Whoopsies. We'll edit that out, no worries. Because initially we set, here's our two coefficients. Omega naught. Our A is going to equal 1.5, correct? And then our omega naught is going to be 7 rads. Okay? This is just our play field, whatever we want to call it. Play field, whatever. Okay, there we go. So now the next thing I need to do is, I'm just going to use capital B, capital A, okay? And now I don't have to worry about this convention. Okay, we're good. We are good. I'm going to do the following. You tell me if I'm wrong. Okay, let's see if this works. And then let's see. Control this. Get rid of that. Whew, it ran. What's H? 1 by 21 double. So here's a problem, is that we're only running real values and we need to run imaginary values. So I don't like this. Let me see. Why are we using polyval? Because that's not the way I want to do it. We're going to do this. S real is equal to 10 minus 10, 1, 10. S imaginary is equal to minus 10, 1, 10, right? And then we need to have H, right, is going to equal some play field, zeros, which is going to be the size of S real, right? And size of S imaginary, correct? So we're just setting up our memory, all right? Whatever this is going to be, like a 21 by 21 square, right? Is that good? Let's calculate this. F9. Size S real, S. Size inputs must be scalar. Oh. Length. Length. Go. Run, F9. There you go. What's H? 21 by 21. Like that. Now we have a play field. So now I'm going to do this for, let's see. For I is equal to the first point down to the length of S real, right? Is that good? And then for J is equal to 1 length of S imaginary, right? Solve for I, J. Is that good? End. You think this is going to work? I don't know if this is going to work. Let's try this out. Because I want to evaluate at this point right here, minus 10 and minus 10, right? Let's see. Let's see what it spits out, whatever. Unable to perform. Oh, what is it? Oh, there we go. I, right? No, imaginary. Hold up. For I is that. J is this. I plus, oh no, I don't like that. Let's do, okay. I'm going to use two different variables. I'm going to use for K, and let's do L, right? So the reason why I did that is because I need an imaginary number. So I'm going to do the following. So this right here is our real number, right? All right, we're going through all the real numbers, right? And we're going to go through all the imaginary numbers, right? So I need S to be real, right? I need the real number, right? Plus J dot times imaginary L, right? Let's see this one. Let's see, L is equal to 1, F9, okay? Now let's see if this turns imaginary. No, we rewrote it. No, we rewrote it. Okay, let me do the following. Control S, and then how do I clear vars? Clear all. What is J equal to? There we go. We got an imaginary number. So I accidentally rewrote J and I, which are both imaginary numbers, to real variables now. So your code will never work. So I called it K and L, okay? Does that make sense? So I have real and imaginary, okay? Or does this help? Real number. Is that better? I don't know. I'm just trying to help you guys out. Imaginary number, right? Is everyone getting this? Real num, imaginary num, all right? Not too difficult. Now we have this. This is going to be a complex number. Now we have a complex number right here. Cool. And now we're going to just fill in this box, our 21 by 21 rectangle or square. Boom. B. Oh, because I made it in capitals. Capital B, capital A. Index in position 1 is invalid. Oh, real num, imaginary num. I love MATLAB, y'all. There you go. Did it run? H. Woohoo! We did it, y'all. We solved it. We have our full square. Now we got to make it 3D. Okay? So now let's do the following. I don't know if this is going to work. Let's see. H 3D, I don't know. X, Y, Z, and C cannot be complex. Okay. S real, S imaginary. Okay, because this is a real, this is, so it's saying this one is complex and it doesn't want it to be complex. So you know what I'm going to do? 20 log, no, dot times log 10 of H. There we go. Cannot be real. Okay, what's going on? What does this produce? What's this produce? F9? Still complex. There we go. Is that better? 20 log. Yay, it's real. So if I wanted to do that, let me see. What did I say to use? 20 times log 10 of absolute of H. Is that what I did right there? All right. And now we have H3D, but what's our output? Mesh C. Okay, what is X supposed to be? X can be a vector. Cool. Oh. No, it doesn't mesh grid. What the heck? Ew, go away. Mesh C. Creates a mesh plot. So what am I supposed to be doing here? Let me see. M and N, yeah. screw this. Okay, it ran. Okay. Figure 1. Woo! Is that it? Whoa. Boy, that doesn't look right. That doesn't look right at all. Let me see. Oh. We need to be negative numbers. So we need to go to our negative numbers, right? This needs to be negative. This needs to be negative. It's always going to be positive. Anyways, let's see. How do I get these numbers to appear here? For real number. Okay, so let me just do this. Let's do K, okay? Let's do L, right? Because this is the real size, right? This is for this H, correct? K, and L, right? So now I just need to figure out what to do with this, because now this is the real size of this, right? But I need to punch in these numbers, these guys right here. So if you know what I'm thinking about, I think I'm going to do this. Oh. S, real. What do you call it? S, real K. There we go. And this is going to be S, imaginary L. There we go. Is that good? So now what I'm doing is I'm pulling the actual number. So if K is equal to 1, right? I'm pulling the first number here. So what is this? Negative 10, right? So now if K is equal to 2, right? I'm going to do it again. Minus 9, all right? So what happens if I do 0.1? 0.1, right? Now I have a better precision, right? I'm going to run this again. F9. Boom, right? And now if I try to do that again, right? K is 1, correct? S real is 10, right? What's going to be K equal to? Minus 9.9. Let's run this. Oh yeah, let's go! You like that? That is your Laplace transform. What is that? That looks cool, right? And if you flip it like this, I wish there was a way to draw the axes, because there can be a way. You know what I'm going to do? Hold on mesh C, or no, not mesh C. S, real, S, imaginary. And then I want to draw ones. So I think what I'm going to do is, because I want to draw axes, but this is technically it. You see from here? Let me just do this. There you go. This is our, what do you call it? Our real values, right? This is our imaginary values, correct? Better yet, let me do this. X label, right? Real axis. Or what do you call it? Re of S, right? From what we did in class. Y label. Imaginary S, right? What the haze? Oh, screw you. Invalid expression. Check for missing or extra characters. Where? Line 29. Oh. There you go. Is that better? Well, this is flipped. Because the x-axis, right, is our real. Our y-axis is imaginary. Something went wrong. Let's see. Because this is wrong. This is not how it's supposed to be. It should be like this. Something happened right here. Okay, this is that. Polyval, boom, boom, boom. Is anyone seeing what I'm doing? KL. I don't want to say it's this. This is not right. No, this is not going to change at all. Y label, and then I guess that's it. Because this is what it would look like. This looks better. Okay? See, now your poles are over here. This is the real axis. This is a real stable function. Grid. You see those poles? Now we got to find the residues. Okay? Anyways, log 10. Let's see what else we can do. And then let me show you another thing. And I think that's where, remember how we can play with these numbers? Let me show you this. Who wants to create a system? Minus 2, minus 3, whatever. 0, minus 3. Boom. And A. Minus 2, minus 4. Remember that guy? Let's run it. Whoa, what the heck happened? Just have a fat super pole. Oh, did I make a double pole? No, that's not what I want. Well, it's saying that we have a pole right here, minus 2. Maybe if I do minus 6, I don't know. Oh, doesn't like that. Come on, what the heck? I'm trying to get the assignment done, man. Give me a second. Let's see. Am I doing this right? Minus 1. Okay, it's saying if you do the following. Minus 1, and minus 2, minus 3. Okay, something's wrong. Let me check this. Okay, there we go. This is another system. And then let me just tune this down, okay? I'm going to tune this down to 5, minus 5 and 5. 5. Is that better? We can zoom in. So it's saying we have a pole at minus 3 and minus 4, okay? Why? Okay, that's our pole going down there, okay? That right there is minus 4, okay? You like that? No, that's a 0. This right here is a 0. This right here is a pole. Yeah. What the heck going on? 1, 2, 3, 4. 0 at 1, S2 at there, S3 there, and S4 there. Did I do this right? Hold up. Because I want you guys understanding what's going on. You guys seeing what I'm trying to do? What I'm trying to do? Let me just do this. 0 or at 1, there we go. A pole there and a pole there, but it's not happening. That's not what I want. Oh, man. Something's wrong. Because that right there is a 0, right? Just going down to 0, and this right here is our pole. That's what I'm trying to show you guys. Grr. See, log 10, that's that. Power. Using the frequency response. I feel like something's wrong right here. That's what I'm trying to solve. Let's see. Got our real. We're calculating every value. Here's our B. Here's our S. That's our play variable. There's that. There's that. You know what I'm going to try and do? brute force this. H is equal to S. What do you call it? S real mesh grid. It's going to be S. I'm just going to call that that. S plus A, right? Dot divide S squared plus 2 dot times A dot times S, correct? I'm just brute forcing it, okay? A dot times squared plus omega naught squared. Okay, that's our brute force method, right? But now I need to make sure this S is complex, okay? And I needed to calculate every point and value. So if I wanted it to calculate, yeah, let me see. Because this right here is our brute force way of doing it. I'll get this. Mesh grid. Oh, no, I don't want to do that. Real. S real dot times plus S imaginary dot times J dot times. Because this is right here is what's going to give us a power, but this needs to be the square. Something's wrong with this. I'm not liking what polyval is doing. I want it to calculate this. Let's see. For K is equal to 1 length. I'm going to copy this one. I want to give you guys this answer. Okay, we're going to brute force this, okay? End, right? But what I'm trying to do is S is going to be equal to this right here, right? Is that correct? Okay. So it's going to be minus 10 and then J minus 10, right? And then we're just going to brute force this right into this square, right? And then H of S, I'm going to do this. K and L, right? Is that good? Let's get rid of this. Okay, we have H of S. Boom, run that. Contour not rendered for non-finite. Okay, that's completely fine with me. Get rid of this. H of S. There you go. Whoa. Okay. Let's see. 1, 2, 3, 4. There we go. Are we getting poles? We are not getting poles. H of S. Absolute value of this log 20 times S real, S imaginary. What is going on? Let's see. Let me change this. Get rid of this. Control R. Control T. What? Okay. 10. 10. 10. 10. I guess we're getting the same answer. I guess that's it. Yeah, I'm giving you guys the real answer. Everything is about the poles are at 2, and then you got this complex. That's a 0 right there. Is that a 2? Is everyone understanding what's going on? So I think what I was trying to do was I wanted to show you guys you can dance with these poles. And that's what I was trying to do right here. So I was like trying to invent our own system. So like you can explore it, okay? I wanted a pole at -3. I wanted a pole at minus, I don't know. I wanted this. I wanted to create our own system. Just see things dance around. And did it do stuff? I don't know if it did stuff. Let's see. H of S. Okay. H of S. Yeah, we did it correctly. Yeah, that's crazy. Okay. Here's our B. Here's our A. And we're running this into here. H of S to H. Yeah, this right here is brute forcing it. So I think the way we did it the first time was completely fine. So, whatever. I'll give you guys these equations. You guys can play them for me. This is what I wanted to try to do. Because we want to be able to simulate whatever circuit we want, okay? This right here is what we want, right? We got our B's. We got our A's, all right? I want to design. I want this to be 5, please. Man, maybe I'm not designing these good poles. Well, if you think about it, let me show you. This right here is a 0 at 1. Yeah, 0 S1. 0 S1, 0 S2, 0 S3, 0 S4. Yeah, hold up. Yeah, this is not making sense. Hold up. No, now I'm angry. Is anyone okay if I call this endpoint? Or I don't know. I'm too lazy. Right? And then I can just design it. Endpoint is equal to 5. Because that right there is our, what do you call it? This is our pole, a 0 at -2, and this is our pole at like 1. Is everyone understanding what's going on? 0 S1, pole at S3, S -4, what? None of this is making sense. What incarnation? I really want to get back to how you guys are doing this, so I'm going to have to research that. Anyways, let's go on to the next problem. Frequency response, okay? So now we got to make this thing wiggle, okay? Using the Freaks function, calculate the frequency response, hj omega, from 0 to omega to this 100. Plot hj omega in dB and the phase, okay? Note that this plot should be a slice of example 1 where we can analyze. Yep, there we go. All the real values are just equal to 0. So if you wanted to, h omega, right, is equal to, what did I tell you to use? Freaks S of B, A, and omega. Calculate the frequency response. Okay, let's see what happens. Figure 2 or 2. There we go. Hold up. Let's see what this does. F9. Oh, W, which is our play variable, which is 100. No. 0 to 100. That's good. Run. We got an h omega. That good? Now let's do figure 2, plot omega, h omega, right? Did I say to use the plot function? Semi-log x. There we go. Title, my freak response. Yay. I don't like that. Oh. Get rid of this. Get rid of this. Boom. Boom. What happened there? What's going on? Hold on. Here's my endpoint. 10. There we go. That's figure 1. Good. That's my frequency response. Okay, what happened here? Was I not supposed to do that? No, because you're supposed to see the frequency response. Let's see. Let's run this again. Because if I started here, I'm going to see a 0 right here. And then as I go forward, it's going to look like a resonator from here, okay? So we should have 0 at DC, but we're not getting 0 at DC. We're getting like 0.44. See, omega, 100. Something's wrong, y'all. Omega, 0 to 100. Supposed to put 0.1 or something like that. Oh, there we go. There we go. That's our resonator. Why did I not say to use 0.1? 20 dot times log 10 of h omega. There we go. There we go. Whew. Does that look like a filter? Right? So, semi-log. Let me show you what I'm trying to do. I'm going to show you this. 0 to 10, right? Okay? And I'm going to just do plot, okay? There we go. Let me just do this. 0.1, correct? Let me just do this one last thing. I'm trying to open your guys' eyes to what I'm seeing, so that it helps you out. Let me get rid of this right here, this statement right there. That's an ugly one. I don't like that. Okay. 0 to 100, 10, 20 log. Okay, I guess I kept the 20 log. My log of x, plot, there we go. There's the plot. Because I was trying to show you guys, okay, you see how there's no log there? It's a simple thing right there. And 0.1, there you go. You see that there? I was trying to show you guys this. Where if you looked at it, it looks like it's peaking like this. You see that right there? 0, and then it does that. That's kind of what this is doing. See? Like that. And that dash right here is going to have some type of residue. That's what you're going to try and find, okay? See how they kind of match side by side? See? Now when if I were to do this as semi-log, well, you can't. This is what I meant by semi-log. Semi-log x. That looks like a filter. Does that make sense? So if I were to, do something funny right here, like make this like, this is DC, this is 10 hertz, 100 hertz, right? So our resonator is about like, where's our resonator? It's about somewhere right here. I would change that x-axis, honestly. But yeah, that's pretty much it. X label is frequency in hertz. Y label is 20 log 10 H omega. There you go. Looking better? So you see, that's what I was talking about, the resonator, okay? So this is not letting anything pass here, but you'll see ringing right here. So that means our response, you're going to see when you do a step response in this or an impulse response, you're going to see a wiggle, all right? So there's going to be a sign in here, or cosine, which from here, you have complex poles, right? Which means you're going to have this wiggling resonator, okay? Does that make sense, everybody? And then let's go to see if I can do your next problem right here. And then I'll tell you this, after this, it becomes easier just understanding. Do your zeros and poles from exercise 4 agree with exercise 1? You may want to play around with your figure. Transfer function to zero pole, generate the factor form, and then using the zero pole, the transfer function, convert the factor form. Yeah, this is not that bad. Honestly, it's just pretty much straightforward, okay? Is there any questions about this? And then this controls toolbox. Draw and label a direct form 2 block because you guys going to be doing some, system. Better yet, let me see. I don't think I told you how to derive it. You're going to be using these equations. Oh, come on. There you go. And then you can create a system based on this, okay? Transfer function, here's one transfer function, here's a second transfer function. You can multiply the transfer functions, okay? And then else, it's the same system, okay? Yeah, literally the same response. So guess what your answer is? Your answer for the second half is going to be the same as the answers to the first half. So how do you verify? This is kind of your verify with LT Spice, quote, quote, because now you're using the controls toolbox, okay? Zero poles, DC gains, impulse response, step response, system model. Did I tell you to do an impulse response? Use the residue function, generate this. Yep, generate the impulse response, right? And then convolve. Yeah. So guess what? Yeah, literally the first half, all this right here, is going to be equal to the second half. So now you have a proof of like, hey, if the first half is correct and the second half is correct, if they look the same, you should do right. I'm assuming everything from the controls toolbox, this right here is your answers. All right, so generate that, okay? And compare that with the first half, all right? Any other questions? Yes, I'll be giving you guys this code to head start, okay? All right, have a good day, everyone.